All right, welcome to PyCSE. I'm going to talk about caching expensive function calls today, and this is a solution or a problem I have in running expensive quantum chemical calculations or other kinds of expensive function calls that could take, even if they take a minute, and if you have to run it 60 times, then you're going to spend an hour waiting for that function. And if the function value doesn't change, then it's really natural to think about caching it so you can look it up later. Now, there is functools.cache in Python and the LRU cache, but those are not persistent. By persistent, I mean it saves to disk, so I should be able to, in the solution I need, close this session, close your notebook, close your script, whatever, go away for a few days while you do the rest of your job. My day job is being a professor. And then when I come back, the cache should still be there and still be usable. So for this, joblib is one of the standard tools for doing it. And so I'll show you a simple example here. You import joblib, we'll import memory here, we specify a location to store the cache, then it provides a decorator for your functions, so you use @memory.cache, and this will run the function once and save the results, and then the second time you call it, it looks up the cached value. All right, so let's have a look. I'm going to run this, and what we're seeing in here is if you see this string with the slow snail, that means the function was run, and if you don't, it was looked up in the cache. So you definitely see here, we ran it once and it printed 4, but the second time it does not run the function, it looks it up. Now, how did that happen? Over here in the little finder, you can see there is a joblib cache directory that is here. It wasn't there a minute ago. And inside of here are some folders, and inside of here is another folder named fun. That's because this function is named fun. And inside here is a hash looking thing. If you're used to GitHub or Git, you'll recognize this as a hash. And finally, inside of this is where the output is stored in a pickle and metadata is formed there. All right, so that is where all of this stuff got stored, and you can see already some potential for challenges with the folder names that are here. All right, let's take a look at another one. This is going to be another function. We decorate it, and it has an optional argument. So if I run this, here what we could expect is the first time we run it, the second time uses the same arguments, so it should call the cache, and the third time we change the A, and so it should run again. So I'll run this, and that's what we see. It definitely ran twice, and we have this, and over here, if you look inside our joblib, now there's an extra folder that has some different things in it. All right, so under here is F2. There are 2 hashes, one for each set of arguments, and 2 sets of results that you could look up. All right, sounds good. Here, if I run this in another cell, then we just get the results. It just looks it up in the cache each time. So if each of these was expensive, then I would save all of that time with the cache. Sounds wonderful. All right, but it doesn't take long to find out things start to go wrong if you don't follow some, maybe you could call them best practices. So let's take a look first at an uncached version of a function that uses, I'll call it a global variable. A is equal to 3. It's defined outside a function, but used inside a function. Running this, not a surprise, here we get 3 times 2 squared is 12. If I make a equal to 0 and run that same argument again, then also no surprise, we get a 0, right? The a is used inside the function but defined outside. Now if I cache this, things look good to start, right? I cache this, has a new function name, so it's different than before. We can run it once, but then retrieve the cache 2 more times. Now here's where things go wrong, right? If I set a equal to 0 here and rerun these, I would expect to get 0. But in fact, we get 12 because the cache doesn't change in this case. The joblib does not detect that a equals 0, and that should invalidate the cache and cause it to rerun. So cache invalidation is one of the hard problems in computer science, so it has bitten us in this particular case and just given us straight up the wrong answers. That's bad, and probably there's a bug somewhere in the world because of that. All right, how about this? Running functions with mutable arguments. If you've been programming in Python long enough, you know that's a bad idea, but it's not always obvious you're doing it, and it has an impact here. So I'm going to show you an example from molecular simulation. We're going to create an atoms object, just a bulk palladium. We're going to run a calculation on it, and we'll cache a function that takes the atoms argument as an object and just calculates, calls the potential energy function. Nothing obvious here that we have a problem. However, when I run this, you can see from here that it was run twice. So it ran once here and once here. And that's a little bit concerning because the whole point of the cache is to avoid running an expensive calculation twice. And if this was a DFT calculation, then we would be waiting, hours for each one, which is definitely bad. Now, what happened? How is this possible? What must have happened is that the hash associated with the atoms in this call is different than the hash associated with the atoms in this call. And the only reason that could possibly be is that the atoms were mutated by side effect when we ran this. I'll show you that that's exactly what's happened here. If we start over, we get an atoms object, and we look at the joblib hash of the atoms, and we look at this particular attribute. What you see is we get this hash, and this attribute is empty. However, just by running this single function here, what happens is the hash changes, and it changes because the results get added to the atoms object itself. In other words, the atoms object is mutated by running it. And that mutation changes the hash of the argument, which changes the hash for joblib, and it thinks you should run two different things. There is a lesson here. Don't use mutable arguments, but the other message is it's not obvious until after the fact that that's the case here. All right, this one I thought was just on principle this should work, but it doesn't. So I thought on principle, if I have exactly the same function here as I did in a Jupyter notebook, that it should be able to look up the cache from the same place. Oh, that's interesting. Maybe this has too many job lists there. Let's double check. Nope, it has 2. All right, that's a strange choice for me. I guess I typed it twice. It doesn't really matter. Okay, this is the same job cache, the same one that is here and here. That's why it's double nested in here. That's my fault for double naming this. But since we can load this, it seems like this should be able to run and load it from the cache. But you can see here that it definitely ran, and even worse, it runs every time. So that means that this is a persistent cache, but if I run this from a script, I don't get the benefit of the cache. So let's see what's happened. If I look through here, now you see there's a different kind of style of folder. So joblib is using the file name it thinks that the function is in as part of the path to save it in. And apparently when I run this as a script through org mode, the file name looks different than when I run it through a Jupyter notebook. So even though these functions are identical, they don't use the same cache because they appear in different paths. So let's see if we can find one of those F4s. Here's one. You can see the hashes are actually identical here and here, but they're in 2 different places, and joblib doesn't do the right thing in my opinion. It should look it up by this, and it doesn't. All right, that was their choice. It's not the one I would have made, but it means that you can't use this cache in different ways, even when it should be the same. All right, and here's my final kind of struggle with joblib. is it is too fragile. Joblib uses the function source in its hash. That means it tries to get the actual string that represents the function. Now the great thing about that is it is always correct. The bad thing about it is you can make any change at all to the function, even adding a comment, changing a docstring, anything like that, and it will invalidate the cache. So let's have a look. So here we ran it clearly once. Let's just try putting in a comment. Right, that is going to make it run again, even though this comment has absolutely no effect on the output. And even adding a docstring is also going to result in having it run again. Now, how do I know it ran again? If I run this now, then it doesn't do that, right? But if I just put a period here, it will rerun it because it is using the actual string source as the hash, part of the hash. So all of those things lead me to joblib is not quite the tool that I want for the kind of persistent file-based cache solutions I'm looking for, where I want to be able to take the same source, the same everything. It needs to be portable so that if you ran this code here, it would be exactly the same hash on your machine as on my machine, so it would be portable and not include information like these temp variables, temp folders, specific user-specific paths here. None of this is portable across a team. So what I did was try to work out some ways that I could solve this. And so I wrote HashCache, and it builds on joblib because joblib does provide a lot of very good support for this problem. They just do some funny things in there. So this is should be available in PyCSE. You should be able to pip install the latest version. The latest version is 2.2.1 now, and it has this HashCache in there. I also use it as a decorator. So we import the decorator here. We specify a directory to store the cache in. I recommend an absolute path in case your code changes path here and there. And I'm going to set verbose equal to true for now so we can see what happens. All right, we use it the same way. You decorate a function here with HashCache, and here we have some h1 is the name, take x, we'll print something the first time, and the second time we expect to not see it. All right, so this is with verbose equals true, just so we can see what happens. This is telling me it wrote to this cache. This is the path that we looked at. Let's see where it is over here. Let's close this one. Here I store this in a kind of Git-inspired style where this is a pickle file that is storing the results, and instead of storing all of these in one directory, I store them in subdirectories that start with the first two characters. Here is some interesting things. So here it says argnames is print, which is not what I thought would happen. I thought it would say X up here, and so there may be still some issues to think about in what I did, but it shows you what kinds of things were done, and then down here it says that it's reading from that cache, and then here are the two results. All right, so let's see what happens if I comment this out. That does change things. Oh, it does. It changes things because it changes the actual function, and then we can see that we have an arg of 2, so something's not quite right in this. But if I put it back, then it's just reading from the cache. All right, I'm going to make this false so that it's more like what we saw before. Now, what problems did I end up solving? So remember the problem I showed you with global variables. Here, if we set a equal to 3 outside the function and use it inside the function, then you see that we ran it once, but then it's reading again. And over here, you can see inside of our cache, we now have these new things that have been, new folders that have been created. If I change a equal to 0 on the outside and run this, I would expect all of these to return 0. And that is what happens. So you can see that it does run a new job because it has detected that the environment in the function changed and it's no longer equal to what it was before. And so it runs again. All right, so one problem solved, we get the right answers. HashCache does a better job of detecting that external change than joblib does. All right, how about the mutable arguments? HashCache does not solve the mutable argument problem, but it does warn you when it happens. So this is the same problem that I showed you before that ran twice, and what it still runs twice, but it warns you that something has mutated and future calls don't necessarily use the cache. Let's put in a third one here. So the third time actually works because the third time the results don't change, and so you end up getting that the hash is a constant. So I didn't really find a way to solve the mutable argument problem. It's not really a problem for your library to solve, but I do like that it tells you something changed. Okay, how about reusing the cache when you run different ways? I think that I solved this one, but we'll find out in a moment. So here we have run this one before, and we get a 4 and a 4. What I thought would be helpful is if I run this in another Python script, or potentially in another notebook, that we should be able to look up the cache the same way. So from here, you can see that that is what happens. So we are able to leverage the fact that this function is the same as the one that's called up here from two different sources and use the same cache to look it up. I think that's a big deal, mostly because we'll be taking advantage of this in different notebooks on different machines, and I want to use the same cache for it. Okay, how about insensitivity to unimportant changes? So it annoyed me that minor changes like comments and doc strings invalidate the cache for joblib. That's too fragile, in my opinion. Why is it too fragile? Because I do a lot of work iteratively where I first write the code and then go back and add the documents or comments. And if that triggers a rerun of your job every single time, it means you have to write a perfect function first, and that probably doesn't exist. So let's have a look at what HashCache can do. So here we're looking up this old function that we wrote. Let's add a doc string. Now, if this was joblib, it would trigger a new job, but here it doesn't. And I'll talk about why in a minute. We can also add comments. You can change the white space, add spaces like this, and none of those will trigger rerunning the calculations. That's because I do not use the source code for the hash for two reasons. One is it's too fragile, and any change will change the hash. The other is it's not always easy to get. In the best case scenarios, inspect will give it to you, but in other scenarios, inspect doesn't work. And what I found did work is to use the function bytecode. Now the bytecode is not sensitive to things like doc strings and comments. It just ignores it or leaves it out or isn't part of it. And so here, as long as your functions have the same bytecode, then they will have the same hash, and then they will have the same everything. All right, so let's see, before I talk about is it the answer, let's just look briefly at what is done in here. So this does build on joblib. I take advantage of that. I especially take advantage of joblib hash, which is able to provide me with a hash of kind of arbitrary Python objects. The objects that I use include the name of the function. I thought it would be convenient or confusing if you had functions with different names that map to the same hash. So I left that in. It uses the name of arguments, the name of other arguments, that includes things that are the outside. That's how I got to the global arguments working. And then here I look at the value of those things. So I try to get the variable value from this globals dictionary. Then this is the bytecode, and then we keep a track of the arguments and the keyword arguments, and we use an sh1 hash. So that's how we get a hash for any function evaluation. It does depend on the name, the bytecode, the value of the arguments, and variable names. So if you change those things, you can expect your cache to get invalidated. The decorator is kind of simple, I think. We get a hash for the function, the arguments, and keyword arguments. Look up the cache, the hash directory, the hash path. There are some options for doing a dry run, for deleting cache entries. If you're not doing that, we check if the file exists, and if it does, we read it. And if it doesn't, then we run the function, get the value, and over here save all of the data. And it's saved with joblib.dump, which is kind of like a pickle file, I think. And that's it. So that's all there is to it. It's very simple. It's just a different set of choices than joblib makes out of the box. All right, back to is it the answer? Probably not completely. This is maybe a week's worth of hacking around, trying things, and learning what the limitations of trying to cache things are. It's a hard problem to solve. There's probably other ways you can break the cache invalidation problem here. And if anything, the big message is if you're going to use a cache solution, then you need to really test it thoroughly to make sure it's not introducing some new issues in whatever you're trying to do. All right, that's it. I thought it would be interesting to talk about and kind of go through some of the challenges in caching expensive function calls. And certainly there are best practices like not using mutable arguments, not using global variables, using functions that only return things and don't work by side effects. Those are all ways that something in a cache cannot go right. And so you should keep those things in mind if you are trying to go down this road as a solution. All right, thanks for listening, and come back for the